So the key for this one is you should be using that Lebanese notation for it, because your P is like what's changing, right? But the population, like P is what you're trying, is like the Y. Do you know what I mean? Like what your function is for. But then in your function, you also are talking about how that exact population is changing. So the way you would set that up, it would be dp dt, so the change in population over time equals. Now I get the 1.2 because you're like, if you're thinking about increasing, but it's not a function, it's a change. It's like a changing, it's a derivative. So like the amount of things that are changing is it's 20% of the population. So you would write 0.2 times the population. It actually might make more sense once we go down to this question. And then minus 10. The reason it's not 10,000 is because P is in thousands already, right? So the 10,000 is just for 10. All these units are per year. Like that 0.2 is the per year unit, and then 10 is the per year. So this is representing how much it is changing. So what's nice about what we're going to do for Euler's method is like there's not an equation for like rates all the time. A lot of times they just are given data. So it's like you have a bunch of data points. So like in Hidden Figures, they just had a bunch of data points of where things were in space. And they use this model to get a very accurate like vibe of how things are changing versus like coming up with like a legit equation. So like if things are changing too much, it's hard to come up with an equation for that. So Euler's method works because it kind of allows for more of a variable change, if that kind of makes sense. So like this one in part B, scientists started modeling in 2010. The estimate that initially there are 60,000 fish. So use your model to approximate the number of fish after 1 year, 2 years, 3 years. So like essentially this is what's happening. So like year one, okay, we started with 60,000, right? So because we're in thousands of fish, okay, so like here, maybe I should say, because it says at t equals 0, right? Because that's initial, right? Then you would say the population is, I'm going to say 60 because we're doing thousands of fish. So it's just going to be straight up 60. So in year one, so after a year has passed, you're going to be taking your 60 fish, 60,000 fish. And what you do is you're adding in, right? You're going to add in your, maybe I should put this in blue because I was going to do blue and red. Okay. So you're going to take your 60 and then you're going to add in the amount of fish that's happening in the year. So what you're going to do is you're going to take dp dt evaluated at when t equals 1. So 1 year has passed. So what ends up happening is you get your 60 and then you add in a full year's worth of like fish catching and releasing and all that stuff. So you're going to add in the 0.2 times the population 60, right? And then minus 10. Because then that, if you type all that in, now we have more fish happening, right? So it increases by 20%, but then it goes down percent because you only restrict it. So now my new population, if you did the math, it was 62. So now we're at 62,000 fish, okay? Because we added in this change that's happening. So now when we go into year 2, I'm not using the 60 anymore because now my population's bigger. Okay, so now my rate is dependent on like the population it is now. So now for year 2, you're going to take the 62 now because that's what you have, plus, and then you're going to add in the rate. But now the time has happened where you're now at t equaling 2, right? So it's year 2. So then what you're going to do now is you're going to take your 62 plus, and then you're going to plug in 0.2 times 62, because that's your p. So again, I'm getting it from this over here, right? And then minus 10. And you might be thinking, well, t equals 2, like, doesn't that make it like double? But remember, there's no 2 in here. Like, there's no time unit in there. So it is legit for what it's representing. So if you tap that in, you get 64.4. So then year 3, it's like the same thing basically, but now you're going to use the new population, add in your rate. This one, I know the time seems kind of dumb because it's like, well, you're just going up by 1 year, right? So you're going to take the new population plus, and then you're going to add in your rate, but your rate includes the new population. So when I forget Euler's formula, I usually go back to this fish example of thinking like, as the population increases, I use that new number for like the next step. Because every time the population increases, if I'm going to add another year to that, it's like my population's changing, it's growing. I already typed this in, it was 67.28. Remember, that's all in thousands of years. Okay, now this is if we did it every year. Okay, if you think about it, if I were to do this more accurately, okay, think about almost like compound interest in a way, like if you're doing interest that way. But like, if I'm going to do every half year, it changes it just a little bit. And it's exactly what you would think when we do it. So I'll show you in a sec. So year half. So instead of going straight to year 1, I would still start at 60, okay? But for the rate of this, okay? Morning. So for the rate, this is what's happening. Remember, this model we came up with is happening for every year. Remember, the 20% was every year, 10,000 every year. So if you're going up by half years, okay, what we're doing is we have to cut that rate in half, right? So that rate represents what's happening every year. If we're going every half year, we now have to take that amount that's going up by and cut it in half, right? So we're going to go dp dt evaluated at t equals a half, and it's essentially the same pattern. So you're going to take your 60 plus, and then that half the year is because you're only doing half the change for what we came up with our model for. And then you'd plug in your 0.2, your 60, and your minus 10. And then you just tap away and you get 61. Does that make sense? Okay, so if I did every half year, maybe I'll just do maybe one more here. But like if we do, now this would technically be year 1, right? But we've already gotten like a new population, quote unquote. Like this is now, we're in June. So now this half is still going to be happening because we're using the 61 now, because now we're just being more accurate. So you're going to do 61 plus half is still there because the 61 we already accounted for half a year. And then it's going to be dp dt evaluated t equals a half. And then you're going to go ahead and plug in, again, 61 instead. And then again, don't plug in 60 because that was the old population. Now we're dealing with 61. And then you tap away and you get 62.1. Okay. So the formula for Euler's method, okay? The formula for Euler's method, this is like very variable-y, right? This y is like the function name. So we did one for population, so that would be like P, right? So the next year over, so n plus 1, how we're gonna write it. So the next like what we're trying to figure out, like the 61, like trying to figure that out, equals, okay, your initial population or wherever you started with. So this is like the 60, right? So this is the one that's before. Then you go plus, and then that green piece, okay, that's going to be how many times you're applying your rate. So since my rate represented per year, this represents that change. So since we're doing it every half year, what that represents is like, if I put it in terms of X, is your change in X. Okay. And then this guy is going to be your dy dx, because we always multiplied it, evaluated when your X equals your N. And that's the formula, because technically this kind of represents your change in your Y. So it's kind of fancy, you know. And this is the guy. That's him. Do you know he's like blind the end of his life and you're still coming up with stuff? It's kind of wild. Here's like a picture of how it's like used. So like it's essentially like you're using your rate it's kind of like intense tangent lines in a way. So like say this is like the legit curve for the function, but like for this fish thing, I don't have a legit curve. I just have like a new rate of how things are going. So it kind of, as you go on with time, it does start to mimic the curve. So it's not exact, but it's close. So now we got this. Okay, so now this is like not really this is just like a rando, right? It's not like a fish situation, but like they're gonna give you a differential equation. They're gonna give you something to start with. So this is like your population of fish to start. And then what you're gonna do is you're gonna approximate f sub 2 if Euler's method is used using starting at x equals 0 with 4 steps of equal size. So the 4 steps is the way to think about like how many times you're applying your rate. Okay, so this is how you start. I usually do a chart because I think it's easier. If you find this on YouTube or like Flipped Math, they'll have more steps in the chart. I think that gets more confusing in my opinion, but just so you know, that's just like a thing. So here we go. We've got the initial condition. So here we go. There's your initial condition. The first thing then we want to figure out is your change in X. So how many times we're we were doing half years. This one, we're doing 4 steps of equal size. We're starting at 0 and want to go to 2. So all you do is you go 2 minus 0 and divide by the amount of steps, which is 4. So this is going to be a half. So again, that's like how many times you're going to be applying your rate. So each time you go down, you're going to be applying a half. Okay, so for the new a half step. So I want to be starting at 0. And I'm starting at 1, so I'm starting here. But in order to get to 2, I'm going to add in a half, a half, a half, and a half to get to 2. So that's how you kind of figure it out. And then what happens as you go through the table, your y is going to keep changing. So what I do first is like I have my initial population. Now I'm going to figure out my rate. So what you do is you take these numbers and plug it into like the rate formula. So you're going to be doing like 2 times 0 minus y. Okay, and then you're going to get your rate, which is going to be -1. Okay, so now to get your like quote unquote new population, you're going to take your y. So that's like your initial. So you're going to take 1. Then you're going to go plus your change in X. So that's like how we did the fish every half year. So you're going to put a half there. And then you're going to plug in the rate that you got, which was -1. And then you get the answer. So half. So now that half is now like your new y. Okay, so this thing here, come on, this guy is now like your new y, and then you keep doing it again. So now you're going to go, okay, 2 times your x minus your y is going to be your rate. And you're going to plug in your x and your y, and you're going to get your new value, which is a half. Then following the steps, you're going to take your, again, this is like after population after a year, you're going to take your half in for your y plus your step size times your rate. And then this is like your new y or your new population. So this is your 3/4. So this is like the new y. So you put 3/4 there. And then you keep going. So next thing, now we're going to get the rate again, and then you're going to plug it in. So do your rate. You're going to get 2 times your x minus your y. When we did the population, it didn't have x and y in it. It just had the y, which makes sense because it represented a population changing. So we only had to deal with how the population was changing. Since this is kind of a rando example, it's going to have different variables in it. So how do we do this? 1, and then you're going to put 3/4 in because that's like the new y. And then you get 5/4. Oops, 5/4. And then you're going to plug it into, you're going to take your y from before. So you're going to take 3/4 plus step size times the rate that we solved before. And you don't have to use the chart. I just think it's easier to organize it. But you don't have to. You could go straight to this. It just kind of gets kind of numbery. 11/8. And there's your next one. So then at the end of this step, that'll be your answer. Because then I'm going to use these numbers, do all this stuff, and then at the end, that's going to be my answer at 2. Like that's the number I'm going to plug in here, which is how I know I'm done, because I wanted to go up to f of 2. So going to plug in your x 3/2, your y 11/8, do your math, 13/8, and then you're going to throw in this into this formula. So now your new y, so again, this is where the y is, so 11/8 plus step size, rate that I just did the work over there to keep myself organized, and then do your fraction work, which you kind of suffer through if it's no calculator. So you get 35/16 is what I got. So 35/16 is like the answer for that. So then if you were to type that out, if you look at 2, this value, if you type that decimal in, it's a little over 2. It's like between 2 and 2.5. So it like actually accurately represents like the value of the actual curve. So like if you did that first one, like remember the slope was -1. It's like they did this on the graph, and then they got a new value at 1/2. So they used this point. And then they used like the derivative to model like how a tangent line going through that point using that rate. So it was like roughly, it wasn't as steep because what was the new slope? The slope was 1/2, right? And then right at 1, because that was the next x value, they used that point and did a tangent line through it. So it like keeps modeling. And then we did 1.5, and then it keeps modeling the curve. So it's like, ours was a little underneath, but like that's kind of the method of how these things are working. It's kind of fun. Do you guys have any questions where the numbers are coming from? Or are you good? Okay. Do you want to try one? You think you can do it? It's not as many steps. 2 steps. See if you can do it. Why not? Hey? You guys can do it, right? So figure out your change in x first. Okay, wait, just kidding. I realized something. You're going from 2 to 1, right? So you're going like backwards. Do you know what I'm saying? So your change in x is negative. It's kind of like you had a fish population and you want to know what it was before we got it. Do you know what I'm saying? So like your change in x is negative because you're trying to like get rid of the rate that happened over time. So when you're doing these, your like change in x is going to be a negative half. It's like when you're looking at this fish thing, it's like what was the population before it was 60,000. So that's why you want to subtract it. Okay, now we can go. Yeah. You got it, right? You were gone for the start of it too, so that didn't help. Probably not. I gotta stop. This will be your demise. Yep. What did you get? It's called extra credit. Wait, what?
They're saying I don't need to do this.
Correct. Because
Well,
once
it's
you
called
got there,
extra
it's done.
credit.
Oh, okay, got it. Yeah, it's negative 5 ace. Did you get negative 5 ace?
Wait, oh yeah, I forgot my negative.
Did you get negative 5 ace?
I forgot my negative, but now I got it.
Okay.
I put 201 as positive.
Oh, yeah, there we go.
Oh my goodness.
How's the fraction work coming?
I don't do mental
Did you get negative 5 ace?
Oh, because I multiplied.
What did I got negative a half for my first one.
Yeah, so did I. So I got that right.
And then 1/4. Oh, you didn't add 1, silly.
Oh. And then this, okay.
Is it negative 5?
Yep.
Probably, I just multiplied wrong.
Did you get negative 5 ace?
I got normal 5 ace.
Wait, is it?
I don't know why.
Negative, because this is positive.
This is positive 1/4.
Yeah, I erased that. I did it again, but because that would be minus 1/2 minus 1/8.
You got negative 5 ace?
Yeah.
Okay.
Oh, it is negative 5.
Look at there. Maybe we'll do. Yep, 2 more. I have to show you the weird ones. Okay, so you can use it to go back in time. Okay. Is there any questions? This one on no calculator is just pain. You know, it's like Riemann sums. It's painful on no calculator. I've seen it on FRQ and multiple choice. So, I don't know. Okay, now they're going to be weird on you. Okay, so there's F. Oh, thanks. Now I got an integral. That's what I want. Okay, f of x is the length of the graph of g from 0 to x. Okay. Use Euler's method starting at 0 with 2 steps to approximate f of 2. So to make your life feel better, okay, figure out the step size, because that you can at least do, right? So we're doing starting at 0, 2 steps, and we're going to 2. So, I mean, I don't know if you really need to do this, but like change of x, 2 minus 0 over 2. 2 steps, so 1. Okay, so we're just doing 1. So every time your x increases, it's going to go up by 1. Okay, it's going to be add 1. Okay, we're starting at 0. Okay, and this is fun because, like, I don't know what y is. Okay, but, do you see it? Do you know what it is? It's 0. Do you know why? You just throw it in that guy. You see it? That's child's play, right? Just kidding. Okay, so to get the first y, okay, so like f of 0, you're just plugging it into the integral, which actually is not bad because you don't really have to do an antiderivative or anything. So that's nice, you know. Okay, so that's 0 when you solve it. Okay, the derivative. This is also fun, right? Because it's not given, right? But, yeah, you're taking a derivative of this thing. Okay, so maybe I should have that as an f instead of the y here. But, like, there's the equation, right? So if I need to find df dx, right, that's the same thing as f prime. So we're just using a little fundamental theorem where we take the derivative of this. So when we take the derivative of it, we put x in, and then we multiply by chain on the upper bound, which is just 1. So you're left with the square root of 1 plus 6t squared, right? It's just what's in the integral. So that thing is going to go right here in your step.
Let me know when it gets difficult.
Yeah. So, what you're going to do is you're going to plug in and do the whole shebang. So it's just a little weird to get your rates and all that stuff. Okay, you ready? Ready, go. Oh, hold the phone. I did a fatal flaw. This is supposed to be an X. Oh my gosh. I had to plug in the X and I rewrote T. That's embarrassing. Okay, fatal flaw. 6. You should do it. You don't want to? Take it over?
Whoa.
You should. It'd be fun.
Oh my God.
Okay, now we can go.
Oh, she's on the next question.
You're on the next question already.
No, like, no, the next line.
Oh, the next line.
Like or I was like, six. No, he's on. It's 0. It's 6. 6 squared. 36 plus 1. I don't know what I'm doing. I got 1. Yeah.
Why isn't it Friday?
Yeah, I got root 7.
Wait.
No,
He's got a point.
Okay, if you see this on multiple choice, the next step will be an option, just so you know. So, like, if you go to 3, like, if you do this step and get a number, it will be an option. So, just so you know. Okay, last but least, this guy is because they don't give you any numbers for y. Okay, Really quick, really quick. Sorry, this is a long one. So they give you this 3K. Isn't that fun? Yeah, we don't need numbers around here. We don't need numbers. What are you talking about? Okay. We need our step size. 2 steps from 0 to 2. Okay, at least the step size, like, super light. Okay, so 1, oops, I should put that in green. 1, 2. Okay. So, we don't need numbers. Silly. Okay? Let's just go with it. We're cool. Okay? Derivative, you just multiply them. Right? So you get 0 times 3K. That's easy. Look, now we got a number. We're fine. We're fine. Because now we take 3K plus, right? Wait, what did I do for this? Didn't I do? Yeah, because that's the Y. This is the Y. So I put in the 3K plus change in X, 1, times the rate, 0. So my new Y isn't really new. It's just 3K. Bless you. Okay, so no change. No change that year. Okay. All right. Maybe we will not, maybe we'll get a 0 again. Wouldn't that be fun? Let's put in my X. Dang it. My Y. Oh no. And we get 3K. Yeah, we're fine. We're fine. You know? So now you're going to put your Y, your step size, your dy dx, which was weird. Okay. And we get 6K. Yeah, 6K. Cool, I did stuff. Okay. Where K is a non-zero constant, if Euler's method is used with 2 steps of equal size, blah, 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 gives the approximation where f of 2 equals 1/3. Find the value of K. Do you know what you do? You guys are just so smart. Yep. Yeah, just do that. So, 118. There you go. That's it. That's it. That was new. So that one took a while.